nanohub.org.
Online simulation and more for nanotechnology.
Okay, good morning everyone. So I hope the summer school has been going well. I just got back from my vacation and an 11-hour ride, so I'm still trying to get back adjusted to the work schedule, but after a series of lectures here, I'll get back up to speed. So you guys are already dived into a summer school, and today we're going to be talking about nanotransistors. Tomorrow morning I have one lecture to wrap that up, and the lecture sort of moves into quantum scale simulation and NEMO, and then the rest of the summer school is devoted towards large scale simulation and NEMO. So I have a series of short lectures. Some are 15 to 20 minutes, some are maybe 30 or a little more. And what we're going to do is to go through the lecture, and then I'll stop and pause and see if there are any questions. And I hope there are a few. First question I'd like to ask is, how many of you are not electrical engineers? Okay, good. So transistors are important, but I've tried to design these lectures so that you don't need to be an electrical engineer to appreciate it. We'll see how that goes. Okay, so the first lecture is just sort of to set the stage and talk about what we're going to be talking about for the next several lectures. And we're talking about electronics, and really the 20th century was transformed by electronic and microelectronic device technologies. You know, when you think about from the invention of radio to television to all of the electronics that we have today, it's just been an amazing, one of those kinds of technologies that gets invented every 500 years or so. Just had enormous impact. Some people are wondering whether we're seeing the end of it, but I don't think we are at all. The 21st century will also be transformed, but there'll be nanoelectronic device technologies, and transistors will play a very large role in all of this. And the nanotransistor is actually the first true active nano device. You know, there are nanoparticles and coatings used in a variety of different applications, but it's really the first true active device with gain that performs functions. So if you're interested in nanotechnology in general, it's a good place to start to understand how to understand this device as a true nano device. And of course, transistors are everywhere. You know, everything that we take for granted in the modern world, from supercomputers to personal computers to all of the personal electronics that we have these days, the communications and fiber optics and everything that we take for granted, it's all enabled by transistors. And a transistor is an electronic device. So electronic devices were really what made electronics possible in the 20th century, and it started with a vacuum tube, and it started very early. So remember when Thomas Edison was trying to build light bulbs, he noticed that the inside of the bulb got dark, and he speculated that something was coming off of the filament, but that's about as far as he took it. But then the physicist J.J. Thomson discovered that what was coming off of those filaments were electrons. And he got a Nobel Prize for discovering the electrons. And it wasn't very long after that until a fellow Fleming, a British fellow, turned that into an electronic device, a diode, a device that would conduct current in one direction and not in the other, and could rectify a signal, and you could use that for detecting radio communication. And then a little bit after that, a fellow Lee DeForest in the U.S. put a grid between the filament and the cathode so that you could modulate the flow of electrons, and now you had an amplifying device. And then things really took off, and you could use vacuum tubes for all different kinds of applications. Okay, so that really transformed the 20th century. You know, suddenly you had communications. If it had come along just a little bit earlier, the Titanic wouldn't have had its problems, because you know, radio communication was just getting started and wasn't standard at that time. It led to what's called the golden age of radio. You had people sitting around their living rooms for the first time. They could listen to entertainment and concerts and news. And it was used not only for communication, but also the first computers were built with vacuum tubes as the basic electronic device. So this is the ENIAC. It was built in 1945. It had over 17,000 vacuum tubes, and 50 of them burned out every day. I understand one person's job was just to replace the vacuum tubes when they burned out, plug in a new one. So these were powerful electronic devices that enabled a whole lot of functions, but they had some problems. They consumed a lot of power, and they weren't very reliable. So people like AT&T, the telephone company, realized that they needed a different device. A vacuum tube wasn't the perfect device. And there were different devices, and people understood these for a long time. Way back in the early 1920s and 30s, people had sat down and had invented devices that were all solid state. They didn't have any filaments. They didn't have any vacuum to worry about. They would consume less power. They would be far more reliable. So it was, it was sort of clear what you would like to build. And people actually built a few. I used to say in these lectures that nobody actually built them, but I was saying this to one of my undergraduate, my beginning semiconductor device. We teach a course to juniors, sophomores and juniors here at Purdue, and I was telling this story, and I was saying, well, these devices could never be built. And the student came up to me after class and said, "What do you mean they could never be built?" I said, well, I said, that's what I understood. That's why we had vacuum tubes. Nobody was using transistors. He said, well, I live in California, and there's my neighbor is in his 90s, and his name is Heil. And he tells me he built these, and they work just fine. Well, that was interesting, but they didn't work fine enough to displace vacuum tubes. But when Bell Labs got started, it was really a major initiative. The reliability, the power consumption was a huge problem. This is the shining example of directed research. You launch a research program that is going to build a fundamentally new device. They set out to build that device, and they couldn't do it. They discovered all kinds of problems. And mainly the problems were with surfaces of semiconductors and surface states and all kinds of issues that they hadn't foreseen. But they were very clever. The guy up in the upper left, John Bardeen, was a very good physicist, and so was William Shockley, the fellow in the middle. And they were able to figure out what was going on and why they were having so many problems. And in the process of doing that, they were probing semiconductor surfaces, and they were sticking wires down on a slab of germanium. You can see it here. So here's the slab of germanium. You can see why that's still called the base of a transistor, if you're building a bipolar transistor. And there are a couple of wires that are going down that glass wedge on either side that give a couple of other contacts. It looks like a bent paper clip there. You wouldn't notice, you wouldn't appreciate when looking at this device that it was going to change the course of technology. And I don't think they really appreciated it either. But they discovered an effect, and it wasn't the device that they were looking for, but it was a point contact transistor, a different kind of transistor. And they realized that it had gain and that you could do things with it. And they got a Nobel Prize for that work. And it launched solid-state electronics. So it wasn't very long before people were building transistors. And they weren't very good electronic devices. Somebody asked John Bardeen once, what are these things good for? They didn't really replace the vacuum tube the way you wanted. They can't take very much power. They don't work at high frequencies. They're not a good replacement for a vacuum tube. And he said, yeah, you're right. But there may be some things you could use them for. Maybe you could use them for hearing aids, or there's some niche applications. So people started looking at niche applications. And one of the first ones were portable radios. You couldn't lug around your vacuum tube radio if you wanted to listen to music. But with transistors, you could build portable radios and carry them around. This is, I think, the first. This ad touts it as the world's first pocket radio. So you can kind of see she's holding it with two hands. You would need a big pocket, right? But it was, you could do something with transistors that you couldn't do with vacuum tubes, and that was really the secret in getting it started. They weren't competing head-on with an established technology. They were looking for the niches. Well, this was actually manufactured in Indianapolis with a company, Regency, just 60 minutes from here. But it didn't really take off until Sony got involved. And they built this 6-transistor shirt pocket radio in 1957. So I can still remember this when I was a kid. You know, your neighbor had a 6-transistor radio, and then you got an 8-transistor radio. Everyone knew how many transistors there were in your radio. It was really cool. This he called a shirt pocket radio because it was small enough you could fit into your shirt pocket. Now actually the story is it didn't quite work that way because Sony had he had shirts specially made for the Sony salesman that they were, you know, white shirts that had pockets just a little bit bigger than the standard ones so that you could put this radio in. But anyway, that started it all and everything took off. Now, some people will say that, well, what was really important was when people learned that you could, instead of building transistors separately and connecting them all together, you could build them on a single piece of silicon and wire them up on that single piece of silicon. That's what's called an integrated circuit. And that idea occurred to a couple of people, Jack Kilby and Bob Noyce, 2 different companies at about the same time. And then things really began to take off. So when I was working on my undergraduate degree in electrical engineering, you know, this happened. Intel made its first microprocessor, the 4004, had about 2,200 transistors. And people say it's a little hard to make a direct comparison, but people say it's roughly comparable to that first ENIAC, the thing that took up an entire room and had 50 vacuum tubes that burned out. Now I remember, you know, this was happening while I was an undergrad, and I don't remember any of us thinking that this was a big deal, you know. Sometimes it's hard to appreciate things when they happen. It's not until later on that you realize that it was a very big deal. So today we have these modern CMOS chips. This one is a little bit old, but you know, a microprocessor chip will have over 1 billion transistors on the chip. A cell phone chip will have a microprocessor unit, some control logic, a lot of memory, some digital signal processing, some analog electronics to go along with it. And you know, we've really got a very powerful platform for electronics, and transistors make it all happen. Now, I'm just going to mention, but not say very much, and maybe next year in the summer school we might say a lot more about this. People put transistors to different uses. You know, most of the usage till today has been in computing and communication. That's what the predominant usage is. But you can do a lot of things with transistors, and people are doing more and more things with them. So an ion-sensitive field effect transistor has been around for a long time, since the 70s. And you know, the idea here is that, let's say you want to measure the pH of a solution, which is a measure of the hydrogen ion concentration. And this can be very important for some medical applications. So more and more we're going to be carrying around, you know, devices that are monitoring our health or our medical conditions. How could you do that with a transistor? Well, the oxide, you know, and we'll go through this in a little more detail. If you don't put a metal gate on a transistor, the oxide has these unterminated OH bonds. And depending on, if you immerse that in a fluid and you've got hydrogen ions, then there'll be reactions that will change the charge state of those OH groups. Changing the charge on the gate will change the current in the transistor. So if you look at the current versus the voltage that you're applying at that fluid gate on the top, you'll get, say, that black line. Okay. Now, as you change the concentration of H+, it'll change the charge on the gate, and it will change the current. So now you have to, if you, let's see, readjust the gate voltage so that you can bring the current back to where it was, the amount that you have to change the gate voltage at is some shift in threshold voltage, and that shift in voltage is a measure of what the concentration is of the pH of the solution or the concentration of the hydrogen ions. And you know, you can look through some first principles, and the sensitivity is 59 millivolts per pH. So some of you who know a little bit about transistors, that 59 millivolts per decade will ring a bell with you, because it's the same physics that we're used to seeing in transistors, but in another context. And there are some very interesting ideas that people are exploring now to improve the sensitivity by an order of magnitude or two or even more, by exploiting their knowledge of transistor physics to make these devices even more sensitive. So there are going to be lots of applications for transistors, and you know, we're going to be talking about the physics of how they work. So we're going to be down at the details, but just want to give you some appreciation for what they're all useful for. So what do they actually look like? So this one, again, it's a little bit dated, but this is a cross-sectional SEM. You can see the transistor. It's got a source up there on the left labeled. So these are very descriptive terms. So that's an N-type layer of silicon doped heavily with electrons. It's the source of electrons. There's a drain on the other end, and that drain is where the electrons go out. There's a gate in the middle, and depending on the gate voltage, we let the electrons come out of the source and out of the drain. And if you look at the heart of the transistor, the region between the source and the drain and the gate, you can see that this is a true nanoelectronic device these days. 32 nanometer technology is actually, the most current technologies these days are 22 nanometers. So they're even smaller. But if you look at those dimensions, the distance between the source and the drain is about 32 nanometers in most processes these days, 22 nanometers in the most significant ones. The big questions these days are, how small can you make that? What physics limits you? If you look at the insulator between the metal electrode on the gate and the silicon, that's 1.1 nanometers thick or so, just a few atomic layers. It used to be, back when we started the nanotechnology initiative, we defined a nano device as, people wanted to exclude thin films because thin films had been around for a long time. So they said, in order to be a nano device, you have to have two dimensions that are below 100 nanometers. So a nanotransistor qualifies as a true nano device. It's got two critical dimensions that are well below 100 nanometers. So this is the circuit schematic that we use for describing a transistor. Instead of drawing an actual picture of what it looks like, you can see the drain, gate, and source terminals there. Current flows into the drain terminal. And the IV characteristics look something like this. So one of the things that we're going to be focused on in the next several lectures is trying to understand these IV characteristics. And each of those curves is a sweep of drain current versus the voltage between the drain and source terminals with a fixed gate-to-source voltage. So as you increase the gate-to-source voltage, you just go up higher and higher in those steps. There's a region we call sub-threshold, in which no current flows, and then above threshold current flows. If we apply a small voltage between the drain and the source, the current is linear with voltage, so we call that the linear regime, or ohmic regime. And if you apply a higher drain voltage, the current doesn't change much with voltage. It doesn't actually saturate, but they used to in long transistors, so we still call it the saturation region. Right? Increases a little bit, but not very rapidly. Okay, now it's really interesting. If you look back, people first tried to explain these IV characteristics in the 1960s. As I said, the first transistors were these point contact transistors, which were not very reliable. You stuck two pieces of wire on a semiconductor, and if you did it just right, you made a good transistor, but it wasn't very reliable and it was very tricky. And then there were bipolar junction transistors, which again was not the kind of transistor that had been envisioned in the early 20th century. But when people started to learn how to control semiconductor surfaces in the 60s, they began to be able to build MOSFETs. And then some of the first theories of what do the current voltage characteristics of MOSFETs look like started to be developed. And this is the first paper that I know of in 1963. And, it's just amazing how well these people got it. They didn't have computer simulations. These days, we can cheat. You can run a simulation, you can see what the answer is, you can look inside, you can see where all the electrons and holes are flowing, and then you can figure out how to make sense of it and write a simple analytical model. They couldn't do that. They just had to be smart and figure it out. And it's amazing how much they got right. It still works really well. Now, it was based on some simple ideas that had been around for a long time about how electrons flow in a semiconductor. So if on the vertical axis here is the average velocity of electrons. On the horizontal axis is the electric field. So you'd think the stronger the electric field, the more force on an electron, the faster they would go. And if the electric field is small, then the velocity is just proportional to the electric field. The constant of proportionality is the mobility. And that works for silicon if the electric field is less than about 10 kilovolts per centimeter. Okay. If you put a high electric field on, the electrons get a lot of energy. If they get a lot of energy, they tend to scatter in many different ways. That makes it hard for them to go very fast. So in silicon, the velocity just saturates, and you can't make it go any faster. You apply a higher electric field, they scatter even more. You can't make them go any faster. And that limit velocity is about 10 to the 7th centimeters per second. So depending on the semiconductor, it may be a little higher or a little lower. Most of them are in that regime. People are really excited about materials like graphene these days because you might be able to get closer to 10 to the 8th is about the limit of any band structure. But you're always in this regime of 10 to the 7th or a few times 10 to the 7th. But based on those ideas, they could explain the current voltage characteristics. And they developed models for the IV characteristics, and 90% of the books that you'll read now have these models in them, still. So if you look in the linear regime, the current is proportional to the voltage across the drain source terminals. It depends on how far above the threshold voltage the gate voltage is. Depends on the capacitance of the gate, and it has that mobility in there because velocity is proportional to mobility times electric field. And it scales as the width of the transistor, how wide it is, divided by the length, how long that channel is, that 32 nanometers that we looked at. So one of the things you begin to worry about in that is it says the current will go to infinity if L goes to 0. And you say, well, okay, we don't have to worry about that. L will never go to 0. But you know, device scaling is just taking us to incredibly short dimensions. L is getting really, really small. And you start worrying, are we missing some physics here when L gets really, really small? Is the current just going to get bigger and bigger? If you look up here at when you're applying the maximum voltage between the drain and the source terminals, and you're applying the maximum voltage to the gate, how much current do you get? Well, now you have a big electric field, the argument goes. So the carriers are going to go as fast as they possibly can. That's the saturated velocity, and you get these expressions. And as I mentioned, almost, virtually every semiconductor device course that we teach these days will develop these equations for the transistors. Despite the fact that it's complete nonsense, right? It made sense in 1960, but it doesn't make sense for transistor dimensions of 22 nanometers or less today. And the reason it doesn't make sense is that this idea that velocity is proportional to electric field, this is really something that makes sense if devices are long enough. So let's look at that a little bit. There's this thing called the Einstein relation, which you might have heard of, which is a relation between the diffusion coefficient and the mobility. And the ratio of the two is just the kT over Q, which is 0.026 volts. Okay? So if I look at this, people call it an effective mobility of the electrons in the inversion layer. It's about 300 centimeters squared per volt second or so, roughly, silicon MOSFET. Okay. So if I use the Einstein relation, the diffusion coefficient is about 8 centimeters squared per second. Okay. Now, if I know a little bit of transport physics, I know that diffusion is a random walk. Carriers bounce around and they undergo a random walk and they diffuse from regions of high concentration to low concentrations. And they go for a while in a direction and then they scatter and they go in some other random direction. And it's just it's a random walk. So there's a relation. They're bouncing around at the thermal velocity. That's v sub t. They go for a distance lambda. That's the mean free path. That's how far they go before they scatter and bounce off in some random direction. And there's a simple relation between the diffusion coefficient, thermal velocity, and mean free path. And this is what it is. You can check the dimensions. Velocity is centimeters per second. Mean free path is centimeters, so centimeters squared per second. At least it's got the right units. And it turns out it's right. So, since we know what D is, and the thermal velocity is something that it's easy to compute for a semiconductor. It depends on the effective mass, but it's close to 10 to the 7th centimeters per second. So you plug numbers in and you find that the mean free path is about 16 nanometers. Okay. Okay. You can use, we'll discuss this a little bit more later, but you really, we need more than one lecture on this. But I'll just state the result. The idea that velocity is proportional to electric field makes sense as long as you have enough scattering events so that everything averages out and that this works. That means that the length of the region that you're talking about, which is the channel of our transistor, should be many mean free paths long, right? Then this concept works fine. That's what the people used in the 60s to develop the theory of the MOSFET. But today, what do we have? 22 nanometer channel lengths, and they're getting even smaller. So we're in the regime when electrons don't move this way, and you can see that by the 1990s, people appreciated that this physical picture is breaking down. That's not what's going on. These are some computer simulations that were done at IBM in the early 90s, and I'll talk about these a little bit more later. But what you see there is a plot. The line is the bottom of the conduction band versus position in a MOSFET. Each dot represents an electron that's being tracked through the device by the computer. So it sees the electric field, it gets accelerated for a little while, it scatters off of something in some random direction, it moves for a while again until it scatters again, and you just track 10,000 or 100,000 particles through and average the results, and we simulate a device. So if you look at that, we'll look at it a little bit more later, but if you look at the region near the drain, the slope of the energy versus position is a measure of the electric field. The electric field is very strong near the drain. So we said one of the basic assumptions is if the electric field gets strong, there's so much scattering that the electrons can't go faster than 10 to the 7th centimeters per second. Well, you just go in and compute the average velocity at every position just by taking every one of those dots and adding them all up, and their velocity is all up, and dividing by the number of dots, the number of electrons at that position. And you get this plot, average velocity versus position. All right, very complicated. There's 10 to the 7th centimeters per second. In a large piece of silicon, you cannot get the electrons to move faster on average than 10 to the 7th centimeters per second. In a short device, it's easy they move much faster. They're out the device before they've had a chance to scatter very much. So this is some very complicated transport physics that you would think invalidates those simple theories. Okay. Actually, it gets even more complicated, and you're going to be spending the next, tomorrow and Friday learning how to use NEMO, that we're in a regime where quantum mechanics is becoming more and more important. So here's a plot. The white line now is the conduction band versus position. It's just like the black line was before. And what we're plotting here is the energy resolved electron density. So red means there's a high density of electrons. And you can see that the electrons are behaving as quantum mechanical particles. They're coming in from the left, from the source. They see that energy barrier there. And classically, they would just bounce off and they couldn't get through. But you can see some red underneath the barrier. Those are electrons tunneling underneath the barrier. You can see some interference effects that get set up. So there's a lot of really interesting physics going on in these very short devices. And you'll learn how to, we can just take these very sophisticated simulation programs and we can run them, and if the people who have developed them have done their job properly and put the appropriate physics in and handle the numerical issues the way they're supposed to, we'll get the right answer. And in fact, 15 years ago or so, I remember going to a conference and somebody saying, these devices have gotten so complex, it's impossible to understand them. You just run the program and that's the answer. Well, that's a very unsatisfying situation. I mean, how do you know what simulation to do unless you have some understanding of what you expect to see and what you need to do next? So I like this quote. Eugene Wigner was a very good physicist, and somebody brought him the results of the simulation and said, here's the answer. Students do this to me all the time. I ran the simulation, here's the answer. Well, okay. Explain, now we want to understand it. Like Wigner says, all right, the computer understands the problem. How do we understand the problem? And it's very important, whether you're just using somebody's program or whether you're writing one, how do you know that you've got the right answer unless you can make sense out of it? These programs are very sophisticated. It's very easy to set up. You think you know what you're doing. It's very easy to set it up so that you've actually done something different, right? You get and unless you're able to look at the results and say, okay, this makes sense, that doesn't make sense, you won't know whether you've made a mistake or not. So, this is what we're going to be doing in these lectures. I'm not going to be showing you any sophisticated simulations, right? We spent a dozen years doing all of those. What I'm going to be talking about is how we've understood all of those simulations that we've done over the years. And there's really a remarkable thing that happens. These are the textbook, this is the textbook theory. Textbooks need to be updated a little bit. But, this theory is remarkably, it still seems to work. This is what surprises everyone. You just adjust the parameters, the mobility, the saturation velocity, and it still seems to describe the current voltage characteristic of this device, even though it operates on physics that is just fundamentally different from what the people who developed the theory had in mind in 1963. Right? And it turns out all you have to do is to make some replacements. You replace this effective mobility by something I'll call an apparent mobility. We'll explain what that is. Then it works just fine. You replace the saturated velocity by something that involves a transmission and a ballistic injection velocity. Then it works just fine. And actually, there's an interesting question about why, when you change all of the physics, why do you get the same IV curves? Just with some different numbers and things. And we'll talk about that too. But the basic answer is that one thing that hasn't changed is that this device is fundamentally controlled by the Poisson equation, self-consistent electrostatics. That's the most important thing. And that hasn't really changed. So what we're going to be talking about a bit, and those of you that were here yesterday, Professor Dada talked about this. We're going to be talking about how you understand this device as a nano device. How you begin with a sensible understanding of transport and then derive the IV characteristics of the device. And then how we relate that to the 1960 version. So, we understand transport very well these days. There was a lot of work that was done in the 1980s and 90s, and we have a whole different way of looking at transport than we did in the 50s and 60s and 70s. And it involves things like ballistic transport and quantized conductance. So here's a little resistor, and you can see that it necks down to a region W that is very thin. Actually, it's electrically controllable. There are two Schottky barriers on both sides of that, and by changing the reverse bias, you can electrically change the width. Now, it's also a very short transistor. So L, the W over L I talked about, it's not a transistor, it's a resistor. But it's a very short resistor. So the length of the resistor is getting very short. Remember, we worried, you have this W over L, and you worry what happens when L gets very small. When L goes to 0, the game's over, but L gets very short. So what do you measure here? When you measure the conductance, you get this. You can see that as you make that resistor wider and wider, the conductance goes up in steps. Classically, we would just think that the conductance, it's like having resistors in parallel. The wider it is, the more the conductance. But it goes up in discrete steps. And it goes up in steps of 2e squared over h, which is some fundamental constants. And we've learned that the way to think about this is that the conductance is 2e squared or q squared over h times the transmission, which is a probability that it will transmit from the source to the drain, times the number of channels that it's transmitting through. And the way we understand this is as we get wider and wider, we get more and more channels, but they come discretely. We get 1 channel, we get 2 channels, we get 10 channels. That's why it goes up in notches. So this approach to transport is called the Landauer approach. You know, some fundamental ideas is that conductance is fundamentally quantized. Transistors are getting small enough that people are worrying about this. And there's an upper limit. No matter how small I make L, all that's going to do is make it more probable that an electron will transmit from the source to the drain. It'll make T approach 1, the transmission approach 1. Then when L gets even smaller, nothing will change. So there will be an upper limit. So this is a better way to think about transport these days. And, you know, you can begin here and it makes sense for very short devices. And then you can take the limit for long devices and you get the 1960s theory. It's very difficult to take the 1960s theory and say what happens when things get smaller, because it's already made the assumptions that everything is big. So it's easier to start with things that make sense for small devices and relate them to big devices. Okay, so these are the goals of the next several lectures. We just want to develop, you know, very few. I'll show you a few simulation results, but not very many. But what the goal is to develop a simple physical understanding of how these transistors work. And we want to also understand why do they have the same looking IV characteristics? Why do they look so similar to the transistors of the 1960s? And in the last lecture, I'll briefly examine some of the limits of device scaling. I'll show you when all of this starts to break down and when the device becomes a fundamentally quantum mechanical device. And that kind of leads us into, you know, NEMO and where you need detailed simulations to look at how small you can actually make a transistor. Okay, so I think that's what I wanted to say by way of introduction to these lectures. And let me just mention, I've got a whole bunch of them to go through, and you don't want to just sit there and listen the whole time. So they're short. So well, I think they're short. Sometimes you don't know until you give them. But we'll go through each lecture. I'll stop. We'll have time for questions, and then we'll go through the next one. I think I can get through all of these today and tomorrow morning. So we'll go through. I'm going to, first of all, review the traditional model. For those of you who aren't double E's, you can see how we teach double E's, how transistors work. So very simple. I'm going to present a picture of how a MOSFET works as a barrier control device that we're going to be using throughout our way of thinking. Then we'll talk about electrostatics, which is critical. I'll talk a little bit about carrier transport, but I can't do justice to it. You know, I would need a whole set of lectures or a course to do that, but we will review some basic concepts, and I'll state the Landauer approach that we will use. You heard, those of you that were here yesterday, I think you heard more about that from Professor Dada. That's the approach that we will be using. Then we'll do the ballistic model of the MOSFET. We'll compare it to experiments. We'll relate it to the traditional model. Then we'll talk about scattering is what really makes things more complicated. Ballistic is pretty simple. We'll talk about how you think about scattering and transmission. Then we'll develop a model that includes scattering, and we'll relate it to experiments, and we'll relate it to traditional models. And then, as I said, we'll end up by thinking about what the fundamental limits are. Okay, that's it for the introduction. If there's a question or two, I'll take it now.
Yeah, why you are saying that there is upper limit to the conductance in the previous slides, like you were saying, like the first thing that the conductance is quantized. This is the first result, and the second result we're saying that there is upper limit. From where this upper limit comes?
Where does the upper limit come?
Yeah.
So the question was, you know, there are two things I mentioned. One is that the conductance is quantized. And actually, when we're getting into very small devices that have very narrow widths, we're beginning to have countable number of modes, so that's becoming important. The other is that there's an upper limit to the conductance, or an upper limit to the current. Textbook theory says the current goes as W over L, says that the current goes to infinity when L goes to 0. That's not true. It goes to an upper limit. Where does that come from? When the device becomes ballistic, when the transmission is 1, then you can't get any more current. If you make the device even shorter, the transmission can't go above 1. Right? So that's your upper limit.